So one more codal rule we have satisfied. The next step is to calculate the shear force. Calculate the shear force. It is denoted as VU. We have the formula for this, WL divided by 2. Substitute all the values, we'll get 74.51 kilonewton. After this, we'll go for calculation of nominal shear stress, that is denoted as tau V. So this formula is given on page number 47 as per cos 40.1, page number 72. We have the nominal shear stress formula. So page number 72, here is the nominal shear stress formula. Tau is equal to V divided by B into D. Using this formula, we will calculate the shear. So this is the formula given on page number 72, and substitute all the values. After simplifying, we will get 0.55 Newton per mm square. So tau value is 0.55 Newton per mm square. This is our nominal shear stress. After this, we'll go for the calculation of percentage of tension steel reinforcement. For this, we have the formula. It is denoted as PT. We have the formula 100 into EST provided divided by BD. Substitute all the value. Simplify this. We'll get 0.698%. So, approximately it's 0.7. This is our percentage of tension steel reinforcement. After this calculation of PT, we'll go for the calculation of tau C. So again, as per your codal rule, as per page number 73, table number 19, by using PT value and FCK, that is grade of concrete, which they have given in a problem, 20 Newton per mm square. By using these two value, we will calculate the tau C value. So by using table number 19, using this table, we will calculate the tau C, that is shear strength of concrete. So this column is percentage of tension steel reinforcement, which we have calculated. So why we have calculated is, this column is percentage of tension steel reinforcement, and our PT value which we have got is 0.7, and the given grade of concrete is M20. By using these two, we will calculate the tau C. So our value is 0.7, but 0.7 is not 0.7 is not there in this column. So we'll take the near value. So 0.75 plus 0.50. Our value lies in between these two values. So 0.50, we have the concrete value 0.36. 0.48, sorry, for 0.50 we have the concrete value 0.48, and for 0.75 we have the concrete value 0.50. By taking these two, we will calculate the tau C value. So we'll write down here. So I will show here. For 0.50 we have the tau C value 0.48, and for 0.75 we have the value 0.50. By using these two, we will calculate the tau C value. By interpolation method, we will calculate the tau C value. I will show how to do that. So first we will take 0.48. 0.48. Why I am taking 0.48 means it lies in between these two values. So plus I am adding it. Why I am adding is because this value goes on increasing, so that I am adding. And for least value minus greater value minus least value, that is 0.56 minus 0.48 divided by greater value minus least value, 0.75 minus 0.5 into the value which you want to find out, that is 0.7. 0.7 into the least value, that is 0.5. 0.5. Simplify this, we'll get our tau v value is equal to 0.54 Newton per mm square. This is how we calculate the tau c value. So now next step is to compare the value of tau v and tau c. So our tau v value is 0.55 Newton per mm square and our tau c value is 0.54 Newton mm square. So our tau v value is greater than tau c value. So when tau v value is greater than tau c, the shear resistance is required. So we need to calculate. So as per page number 72 cos 40.4, what it say? Page number 72, what it says? Design of shear reinforcement. When tau v exceeds tau c, given in table 19, when tau v is greater than tau c, the shear reinforcement shall be provided in any of the following forms. When tau v is greater than tau c, what they are saying? They are saying we need to provide the shear reinforcement in the form of vertical stirrups, A and B bend up bars along with stirrups, and one more is inclined stirrups. So where bent up bars are provided, their contribution towards shear reinforcement shall not be more than half of the total shear reinforcement. Shear reinforcement shall be provided to carry a shear equal to Vu is equal to tau c Bd. The strength of shear reinforcement Vu shall be calculated by using the formula. This. So we'll calculate. So by using Vu is equal to tau c into Bd, by using this, we'll calculate the shear carried by the. So now we have to calculate the shear carried by concrete, that is denoted as VUC, shear carried by concrete. For that we have the formula tau c into Bd. Tau c value is 0.54, B value is 300 plus 450. Substitute all the values. Simplify this, will get 72,900 Newton. In terms of kilonewton, 72.9 kilonewton. This is the shear carried by concrete. And we also need to calculate the shear carried by stirrups. For that we have the formula VUS is equal to VU minus VUC, shear carried by concrete. Substitute all the values. Simplify this, we will get 1.61 kilonewton. After this, the spacing of stirrup should be done. For that we have the formula given on page number 73. Page number 73, that is VUS is equal to 0.87 FY ASVD divided by SV. By using this formula, we will calculate the spacing of stirrup. So by taking this formula which is given on page number 72, I will calculate the spacing of stirrup. SV is equal to 0.87 FY ASVD. I am moving this to here, that is VUS. So now we need to calculate the ASV, that is area of vertical stirrups, to find out the SV. So again we need to assume the number of bars, so that I am assuming 2 legged vertical stirrups of 8 mm 5 bars to calculate the ASV. ASV is equal to 2 into pi by 4 into 8 square, that is diameter. We have taken 8. After simplifying this, we will get 100.53 mm square, and substitute this value in here and calculate the SV. So substitute all the value, will get how much? We'll get 10,144.94 mm. This is our ASV. As per page number 47 and 48, what it say? The maximum spacing of shear reinforcement. The maximum spacing of shear reinforcement measured along the axis of the member shall not exceed 0.75 d for vertical stirrups. What they have said for vertical stirrups, our value, SV value should not be greater than 0.75 d. They have said. And one more what they have said. In no case shall the spacing exceed 300 mm. They have said our spacing of stirrup should not be greater than 300 mm. By using these two cases, we'll calculate the SV, which is given on page number 47 and 48. SV is what they have said, our SV should not be greater than 0.75 d. So substitute the value, simplify this, we'll get 337.5 mm. They have also said our SV value should not be greater than 300 mm. So our SV is equal to 300 mm. And one more what they have said, our HP value should be least of these three. So the least value is 300 mm. So I am taking our SV value is 300 mm. Our SV value should be least of the above three cases. Case 1, case 3, case 3. It should be least value. So I am 300 is least. I am taking SV is equal to 300 mm. So provide 2-legged vertical stirrups of 8 mm pi bars at 300 mm center to center. So whenever you calculate, if you get more than 300 mm, that is 4000, 5000, whatever you got in your problem, you should provide at least 300 mm. That is the minimum value. So if you get less than 300 mm, that is 250, 260, 280, that time you need to provide which is the least value you got. So I have get 300 mm, the least value. So I am taking SV is equal to 300 mm. This is how we calculate the spacing of stirrups. Again we have satisfied one more codal provisional. After the calculation of this, we'll go for the calculation of tau c maximum. Again by using codal rule as per page number 72, by using table number 20, and also by using the value of FCK which we have given in our problem. So by using G2 we'll calculate the tau c. So page number 73, this row is tau c maximum. This is grade of concrete. So we have given the grade of concrete is M20 mm. For M20 grade, our tau c maximum value is 2.8. So tau c maximum is equal to 2.8 Newton per mm square. Our tau c maximum is greater than tau v. So our tau v value is 0.55. Our tau c maximum 2.8. So the tau c maximum is greater than tau v. So our design is safe. So next step is to check for the deflection control. For deflection control, as per page number 38, figure 4, we'll see. So page number 38, figure 4, by using this chart, we'll check the deflection control. By using this chart, we'll calculate the modification factor. After calculation modification factor, we'll calculate the deflection control. Before coming to this, here they have given one formula. Fx is equal to 0.58 Fy, area of cross section of steel required divided by area of cross section of steel provided. By using this formula, we will calculate the Fs. The Fs is required to calculate the modification factor because this is Fs curve. They have given, for that we need to calculate the Fs. Same formula I have written here. Substitute all the values. After simplifying, we will get our Fs value is 173.26 Newton mm square. This is our Fs value. By using this and Pt value, we will calculate the modification factor. So our Fs value is 173. This is the Fs curve. So 173 comes approximately near to 190 curve. Fs 190 curve that comes here. I am taking this curve by using the Pt value. So our Pt value is 0.7. So 0.7 means it comes near to near to 0.8, so it comes here. So where it touches the curve and stay to, that is our modification factor, and it touches here and stay to this, stay to here. Here is our value, so it comes approximately 1.4. Our modification value is approximately 1.4. So our KT value is 1.4. So now, as per page number 37, cos 23.21, which I have shown by calculate the effective depth in the beginning of the formula, I will show page number 37 what they have said. The vertical deflection limit may generally be assumed to be satisfied provided that the span to depth ratio are not greater than the values obtained below. What they have said, our L by D ratio should not be greater than given. So we are calculating simply supported beam, no? So for simply supported beam, the L by D ratio should not be greater than 20. So I am taking L by D is equal to 20. L by D max is equal to 20 into KT, modification factor. So after simplifying, we'll get 28. And we need to calculate the L by D provided. So our L value is 5300 divided by 450. After simplifying, we'll get 11.77. So our L by D max is 28 and this is 11.77. So our L by D max is greater than L by D provided NC deflection control is satisfied. This is we'll calculate the deflection control, and this is our last step, and next is to design the reinforcement details. Drawing of that. Without the drawing, our RCC problem is incomplete. So this is the beam. So this is the beam having the supports 300 mm and clear span of 5000 mm and effective span of 5300 mm. And this is the anchor bar. At top side there is two numbers of 12 mm pi bars, and at bottom side this is the main bar, that is tension reinforcement. Three numbers of 20 mm pi bars, and these are the stirrups, two-legged vertical stirrups of 8 mm pi bars at 300 mm center to center, and these are the vertical stirrups, and this is the overall depth, that is 500 mm. This is the longitudinal section diagram of beam. Now we will see the cross section diagram. So when you cut the section at here or at the middle or at the center, we will see three numbers of 20 mm pi bars at bottom side, that is tension side, and two numbers of 12 mm pi bars at top side, that is, and this is the stirrups, two-legged vertical stirrups of 8 mm pi bars at 300 mm center to center, and this is our overall depth 500 mm. This is the effective cover which we have provided 15 mm. This is our width, that is 300 mm. This is the diagram of our reinforcement details, and here our problem ends.